Okay, I'd like to start. And today we continue studying a model for associative memory. This is what we started last time. And I'll just write down the model equation. So we have the standard model. R dot is equal to Ri dot is equal to minus Ri plus G of sum over J, Jij Rj, where G of X is hyperbolic tangent of X. And we considered a particular connectivity matrix, Jij, is equal to 1 over n, sum over mu, pi mu, pj mu, jii is equal to 0, where pi mu is equal to plus minus 1 with probability 1/2, and the values of pi and pj in different memory patterns are independent. And the question that we asked is whether these patterns, these vectors, so the vector p mu, this would be a vector of minus plus 1, whether these vectors are attractors of the dynamics. We already know that because connectivity is symmetric, the dynamics will converge to a fixed point. We wanted to know whether these vectors are fixed points of the dynamics, and the answer is clearly no. It's clearly no because the fixed point would be R is equal to G of sum over J of Jij Rj, and this G is hyperbolic tangent. It never reaches plus and minus 1. So these patterns cannot be true fixed points. And then we said, well, maybe these are approximately fixed points. Maybe the attractors of the dynamics are very close to these memory patterns. This was the question that we asked ourselves. And, well, the answer is likely to depend on the parameter beta. So we considered a particular, we started by considering the case of beta, which is very large. So this hyperbolic tangent is, in fact, a sign. So in this limit, at least, these patterns can be attractors of the dynamics. We also considered the case of large network, n is much larger than 1. Finding, identifying all the fixed points of the dynamics in this case is a difficult task because of the nonlinearity. We have n equations and nonlinear equations. We don't know how to solve these equations in general. So we asked a simpler question. We didn't ask, we weren't looking for all the fixed points. All we did was to ask the question of whether these patterns are a fixed point in the limit of beta going to infinity. And the idea is that if they are fixed points in this limit, then we hope that when beta is not infinite, but smaller than infinite, maybe something that is close to these memory patterns will be still a fixed point. And with respect to the issue of stability, we at the moment ignore this issue of stability, and we just ask the question of whether these patterns are fixed points. Any questions? Okay, so the way to identify or to answer the question of whether whether a particular pattern is a fixed point was, without loss of generality, we consider the first memory pattern. And then we want to know whether PI1, whether the activity of neuron I corresponding to memory pattern 1 is equal to the sign of sum over J of Jij Pj1. So if all neurons in the network, if we force all neurons in the network to have a value that corresponds to memory pattern number 1, will neuron I also be, will the input to neuron I be congruent with the desired, with its desired activity given memory pattern 1? This was a question. Or the question is, what would be the sign of PI1 times sine of sum over J, Jij Pj1? And the question, is it a positive? Is it larger than 0? Or if we're just interested in this question, then we can replace it by the question of whether PI1 times the input to the neuron, given that all other neurons in the network are in memory pattern 1, is this a positive number? So we did the math, and we found out that this is equal to n minus 1 over n plus one over n sum of mu from 2 to p. P is the number of patterns embedded in the network. Pi1, Pi mu sum over J is not equal to I, Pj1, Pj mu, Pj1. And this is where we stopped last week. So this is clearly, well, this is almost 1, so this is clearly positive. But the question is, what can we say about this term? This term, which can be, well, we have a sum over many terms, and the question is, what's the value of this sum? So I left it as a question, and after class, one of the students came to me and asked me, well, how can we say anything about this sum, given the fact that we don't know the values of Pi mu at the different patterns? At best, we can say something about the distribution of this term, rather than about the actual value of this term. And she was absolutely right. We cannot say anything about this about the exact value of this term, but we can say something about the distribution of this term. So what can we say about the distribution? Well, before that, any questions? Is this point clear? So what can we say about this term? How many elements are there here? This is a sum of many elements. How many elements? Yeah, so this is a sum over p minus 1 terms, and this is a sum of n minus 1 terms. So here, together, we have p minus 1 times n minus 1 terms, or in the limit of large n and large p, this would be approximately equal to n times p. What can we say about each of these elements? So we have the 1 over n term, but what can we say about these elements? What are their values? So each one is plus and minus 1. So the product will also be a plus or minus 1. So in principle, we can write it, well, also in practice, we can write it as, I don't know, n minus 1 over n, plus 1 over n, sum over k of what I will call zk. Zk is a plus or minus 1 variable. And this sum would go from 1 to n minus 1 times p minus 1. So this is the sum of the n minus 1 times p minus 1 terms that Musa suggested. We know that the products, since all of them are plus and minus 1, the products are also plus and minus 1. But what can we say about the distribution of zk? So let's look at these two terms. So these two terms correspond to the neuron I. This is a neuron I in memory mu, and this is a neuron I in memory 1. But mu is larger than 1. And in our model, all memory patterns are independent. So these two are independent. What about these two? These two are also independent for the same reason. What about pi1, pj1? They're also independent because I is not equal to j. So taken together, we have a product of 4 numbers that are plus and minus 1 with a probability 1/2, and they're all independent. So how is z distributed? It's plus or minus 1 with a probability 1/2. Okay. Okay. So this is becoming easier. So this is approximately equal to 1. And what can we say about, I don't know what can we say about the distribution of this? How is this sum distributed? I'm sorry? Has a mean of 0. Okay. So let's write it here. So the mean of 1 over n sum over k of zk, I'm denoting mean this way because the interpretation of this mean is it's a mean over distribution of memories. It's also known as we'll discuss it later. So this is a mean over the distribution of memories. It's typically denoted by two inequality terms rather than 1. So this is just equal to 1 over n sum over k, the average of zk, which is equal to 0 because this is plus and minus 1 with a probability 0. What else can we say about this distribution? The mean is 0. This is correct. The standard deviation is 1. 1 over n. Whenever there is a disagreement, it's always good to vote on things, right?
It depends if you count the 1 over n cubed or not.
So what's the variance of zk? So zk is plus or minus 1 with a probability 1/2. So what's the variance of zk? 1. So what's the variance of this term? So we have a sum over terms. Each one has a variance of 1. They are all independent. So the variance of the sum is the sum of the variances. And how many terms do we have? So we have n minus 1 times p minus 1. And this is multiplied by 1, which is the variance of a single element, which is approximately equal to p over n in the limit of large P and large n. Okay. We're making some progress here. But remember that the question that we need to address is what's the probability that pi1 times sum over j, jij, pj1, what's the probability that this term will be positive, right? This is what we are trying to compute. What's the next step? So we know the mean, we know the variance. Now we can compute we can go to the third order, right? We can compute zk cube to the power of 4 or 5, and then construct a full distribution, right? So shall we do it? Why not? Should be a better way. Okay. What's a better way? I should call Itamar. Why should I call Itamar? Central limit theorem. What do we know from the central limit theorem? We know. Why can we assume that it's Gaussian? We have a sum of a large number of elements, almost n times p elements. that are drawn from the same distribution, all independent. So in the limit, this will be normally distributed. And it's normally distributed. We know the mean. We know the variance. So we know everything that there is to know, because the normal distribution is fully characterized by the mean and the variance. So I need to give it a name. Let's call it H. Let's call it HI. The input to learn HI. What would be? Let's call it X. XI. So we're interested in the probability that Xi is positive, and we already know that Xi is normally distributed with a mean which is 1 or almost 1, and the variance which is equal to P over N. So we can compute, we can plot X. So this would be 1, this would be Xi, and this would be the probability. So if this distribution looks like this, then the probability of a mistake is very small, because the probability that Xi will be negative is very small. However, if the variance of the distribution is large, and the distribution looks like this, then there is a substantial probability of a mistake, this area under the in the negative part of the Gaussian. And you can see that the larger P is, the larger the probability of a mistake. So we already discussed last time the case of P being equal to 1, and then the probability of mistake is 0. And we, from this approximation, when P is small relative to N, indeed, the probability of a mistake is small. And however, as P increases, the probability of a mistake, or the probability that this inequality will not be satisfied, increases. So we can say that as long so if P over N is much smaller than 1, then the probability of Pi1 sum over j, jij, Pj1, probability that this would be larger than 0 is approximately 1, which implies that all memory patterns, which implies that this particular memory pattern is a fixed point of the dynamics. We don't know whether it's a stable fixed point, but this implies that this will be a fixed point of the dynamics. And if it's true for memory pattern number 1, this without loss of this is all memory patterns are the same, so we expect that all memory patterns will be fixed points of the dynamics. Again, we have not proven that these are stable fixed points, and we have not proven that there are no other fixed points. But at least we expect that if P is much smaller than N, then we expect that our memory patterns will be fixed points of the dynamics. It's often common to denote P over N by the letter alpha. This is also would be considered as the memory load. And this very simple analysis implies that as long as alpha is much smaller than 1, then the memory patterns are fixed points of the dynamics. Questions? Is it clear what we've done so far? So now, if there are no questions, I would like to do something perhaps slightly more interesting and try to answer the question is how much to be more precise about this question of alpha. So the analysis that we did so far is also known as signal-to-noise analysis of a capacity. The signal is this 1. This is a contribution from the connectivity matrix of the first memory pattern, of the memory pattern that we're interested in retrieving. And noise, this term, is a contribution from all other memory patterns in the network. Let me say it again. So we embedded many memory patterns in the network using this connectivity matrix. One of them corresponds to the particular memory that we are now trying to retrieve, or that we're studying its fixed point. So the contribution of this particular memory pattern from the connectivity matrix, the contribution to the input to the neurons in the network is this term that has a magnitude of 1, and this would be the signal. The contribution from all other memory patterns that interfere the retrieval of the particular memory pattern that we're interested in is considered as noise. This noise term has 0 mean, but has a variance. And the contribution, this is the interfering effect of all other memory patterns in the network, and as long as their contribution is not too large, then we can still retrieve the memory pattern. If the level of noise is too large, if the interference is too large, then we will not be able to retrieve this memory pattern. Now, we already understand that the larger the number of memory patterns, the more interference we will have, and the larger is the probability that we will not be able to retrieve the memory pattern. We have an order of magnitude estimate that P over N or alpha should be smaller than 1. But we don't know whether it should be, I don't know, a third, or a tenth, or perhaps 1 over square root of N. And this is what we will try to answer now. So how are we going to do it? So the question that we are asking is, what is the probability of a mistake? I'll denote a mistake with a minus when considering a particular neuron in the network, neuron number I. So what is this probability? We already said that this would be equal to this area under the Gaussian. So this would be an integral from minus infinity to 0 of a Gaussian dz over 2 pi sigma square e to the minus z minus mu squared over 2 sigma squared, where this mu is where mu is equal to 1 and sigma squared is equal to p over n. So we need to estimate this integral. So we can do a simple change of variables. And this would be an integral from, use a different color. This one? Well, let's try this one. Everything will be different in the new building. Be patient. Okay? An integral from minus infinity to minus 1 over sigma dz over square root of 2 pi e to the minus z squared over 2. So this is the probability of an error in a particular neuron for a particular memory pattern, let's say memory pattern 1. So we want this number to be small. And we want this number to be small not only for one particular neuron, not only for neuron I, but for all neurons. So this implies that we will want sigma to be small. So let's say that sigma is equal to 0. Sigma is equal to 0, then this integral is equal to 0, and we're fine. If sigma is infinite, then this integral is equal to integral from minus infinity to 0 of a Gaussian. This integral will be equal to 1/2. Okay, so if the noise is infinitely large, then the probability of a mistake is 1/2. That makes sense. The mean doesn't make any. There's no. In the limit of sigma being equal to infinity, then the fact that this is 1 doesn't have any meaning. And in the limit of sigma being equal to 0, then the probability of a mistake is 0. But how are we going to approximate this? How are we going to approximate this probability in the case of sigma that is small but not equal to 0? So what we are going to do now, we are going to approximate this integral. Turns out that this is something pretty useful, not only when doing neuroscience, but also in economics, in many fields. Knowing how to approximate the area under the tail of a Gaussian is something pretty useful. So that's why we are doing it. That's another reason why we are doing it. So we're trying to approximate this integral in the limit of sigma, of small sigma. So we consider the case of sigma that is small. So how are we going to do it? Any suggestions? So we know the answer when sigma is equal to 0, and we want to approximate it for a small sigma. So what should we do? Taylor. Okay. How are we going to do Taylor? I'm sorry? Let's start with Taylor first. So let's do a Taylor. So this is a function of sigma. So pi minus is some function of sigma. So this should be approximately equal to this function when sigma is equal to 0, plus df d sigma when sigma is equal to 0 times sigma. Right? That's the idea. Okay. What is f of sigma being equal to 0? This we already know. This is 0, right? Because it's being integral from minus infinity to minus infinity of this Gaussian. So this is equal to 0, which is a good start, right? What about the derivative? So that we have the 0. Gaussian. So this would be 1 over square root of 2 pi e to the minus 1 over 2 sigma squared times the derivative of minus 1 over sigma times 1 over sigma squared. This is the derivative. Okay, and we are interested in this at the limit of sigma being equal to 0. So what's the value of this term when sigma goes to 0? It's a Gaussian. We already know it's 0. And this is 0 times, well, infinite. Right? So what do? We use L'Hopital's rule. And it turns out that this is also equal to 0. So we can take a second order in Taylor expansion. But it will not work because in all orders of a Taylor expansion we'll always have this Gaussian term that will be stronger than the polynomial contribution. So doing Taylor expansion was a good idea, but it didn't work. So we need to use a different technique, and the saddle node approximation is actually the technique that needs to be done, but we will not fully do it here. I will just show you how this can be solved for this particular example. So the Taylor expansion doesn't work here. It's nice to know that Taylor doesn't always work. Okay, so the integral that we're interested in solving is the integral from minus infinity to minus 1 over sigma dz e to the minus z squared over 2. So we can do integration by parts. It will be integral from minus infinity to minus 1 over sigma of 1 over z times z e to the minus z squared over 2. And this we can do by we can use the technique of integration by parts. So the integral of z e to the minus z squared over 2 dz, to solve it, we change variables. We use some, I don't know, k is equal to z squared over 2, or dk is equal to z dz, so this would be the integral of e to the minus k k. This is equal to e to the minus k. So this is the first term. So our integral will be equal to minus 1 over z, e to the minus z squared over 2, minus infinity to minus 1 over sigma, minus the integral from minus infinity to minus 1 over sigma, the derivative of this, which is minus 1 over z squared, times e to the minus z squared over 2 dz. So this is integration by parts. This is what we call, this is a u, this is a v prime. So this is equal to sigma e to the minus z squared over 2. This is the first term. What do we do with this term? We can do the same trick. So this would be an integral from minus infinity to minus 1 over sigma, minus 1 over z to the power of 3, z e to the minus z squared over 2 dz. And when we do this integral, we will have the same term as before, but now with corrections of z cubed plus another integral. So eventually, this integral will be equal to sigma e to the minus, forgot to put the sigma here. This will be equal to sigma e to the minus 1 over 2 sigma squared times 1 plus corrections of sigma squared, and then we'll have corrections of sigma to the power of 4, sigma to the power of 6, and so on. So we can write the whole series if we want. But the dominant term would be 1, and then there will be correction of all the sigma squared. So this integral, to the first approximation of this integral is sigma e to the minus 1 over 2 sigma squared. And if you Taylor expand this term, you always get zeros because of this term, because of this exponent. So this is not a unique, but typically Taylor is like the first solution. Here it will not work because you have this exponential term that always gives you zeros. Another way of doing it, well, let's forget the other way. Okay, so now we have an approximation to this term. So we computed the probability of a mistake in one neuron for one memory pattern. But in fact, this is not sufficient because we are interested in the case of no mistakes in none of the neurons. So we computed the probability of a mistake in one neuron, but we want to compute the probability that there will be no mistake in none of the neurons. And this we will do after the break. You can take a break. אלה לא כותבים ואז הם נתקעים? אולי כדאי לזרוק אותם. לא, אבל אם זה... מי אפשר להשתמש? אני אפשר להשתמש? מה? אני לא אזרוק, אבל... אני שטוב לו חתיכה הזאת עם טיילור. קצת טיילור לאינדקס, לדבר הזה, ואז... לא, לא יכול. אם אתה יודע לשמור את האיבר הזה, אם אתה מקבל פה חיסונים, כאילו יש לך כאן איזשהו, אתה תקבל את הפיתוח, אם אתה עושה ניתוח של זה, נכון, אז אתה מקבל תחומים, שתשיגים אותו, יש לך מכפלה של האיבר הזה, שמגבול את זה סירה זהיר, אבל אם אתה מפתח את זה, כן, זה כאן אבל זה יותר מורכבת. נכון, נכון, אתה עושה את האקסטרים שלו, נכון, זה לא יכול לעשות את הדברים המלאים, כיוון אחר. וזה, כן, ברור. Okay, I'd like to start. So, given the technical limitations, I deleted everything and just wrote the important results and changed all the markers. So these are basically the results obtained in the previous hour. The probability that there will be a mistake in neuron I is equal to this integral. And in the limit of small sigma, we came up with an approximation of this integral. And the sigma, this is the variance of the noise, is equal to P over n, a quantity that we also denoted by alpha. Now, this was the probability of a mistake in a single neuron. But in order for a memory pattern to be a fixed point, it is not sufficient that this is small. We need that there will be, it's important that there will be no mistake in any neuron. So what is the probability that there will be no, how are we going to compute it? So what's the probability that there is no mistake in no neuron? So this is the probability of a mistake in one neuron. So the probability that there would be no mistake in so the probability that we're interested in is 1 minus 1 minus pi minus to the power of n. So this is a probability of a mistake in one neuron. This is a probability that there is no mistake in one neuron. This is a probability that there is no mistake in none of the neurons, and this is just one minus this term. We can write it as 1 minus e to the logarithm of 1 minus pi minus to the power of n, or 1 minus e to the n log 1 minus pi minus. And since we're considering the case of small probabilities, this is just equal to, or this is asymptotically equal to 1 minus e to the minus n p I minus, where we just Taylor, this time we Taylor expanded the logarithm. This is natural logarithm. When I write log, I always mean natural logarithm. So the requirement for us is that for a memory pattern to be a fixed point, what we need is that n pi minus would be sufficiently small. How small? Well, it depends on how tolerant we are to mistakes. But we can compute it. So we can ask the question, how many memory patterns can be, or what's the maximum number of memory patterns such that the probability of a mistake in any neuron will be smaller than, let's say, 5%, or 1%, or 0.5%, or 0.1%. But in general, this would be some number that I denote by n, an order 1 number, which can be 1, 2, 3, 5, depending on how what's our tolerance for a mistake. Or we require that pi minus should be smaller than 1 over n times n, where small n is a number, I don't know, order 1 number, and large n is the number of memory patterns in the network. So the question that we ask ourselves is, what is the maximal number, the maximal value of alpha such that this is true? Or what's the value of alpha such that square root of alpha over square root of 2 pi, this is from the integral, e to the minus 1 over 2 alpha, will be smaller than this n times n. So let me repeat the analysis that we are doing. We computed the probability of a mistake in one neuron. So we embed, or we put the entire network in a particular memory pattern, let's say memory pattern 1. And there is some inequalities that should be satisfied in order for this memory pattern to be a fixed point. We computed the probability that the probability of a mistake in one neuron, that this inequality is not satisfied for one neuron. but this is not sufficient. We want this. We want to compute the probability that this equality is not satisfied in any of the neurons. What is this? This is a probability in at least one neuron, and we computed some number. And given for any such for any tolerance, and how tolerant we are, this will be determined by this small n number. We have an inequality that relates p, or more precisely, it's more convenient to write it as p over n, or alpha, which relates this term, alpha, to the inequality. So what we need to do is to find the maximal value of alpha such that this term is smaller than 1 over n over n times n. For example, if alpha is equal to 0, then this inequality is clearly satisfied. This left-hand side would be equal to 0, and right-hand side is a positive number. But this would correspond to a case where the number of memory patterns in the network is 0. We are interested in the maximal value of alpha such that this inequality is satisfied. Now it's kind of difficult to find because we have here alpha in the square root and alpha in the exponent. This is why it is not immediately trivial. So what do we do? How are we going to address this question? Is the question clear? So there are two ways of doing it, or several ways of doing it. I'll start with the more intuitive one, perhaps, and then we'll do it more formally. So more intuitive would be the following. Well, let's consider the case of alpha being order 1. So let's say alpha is equal to 1. So here we'll have order 1 terms. So clearly order 1 terms are not smaller than 1 over n times n. So clearly, alpha should be smaller than 1. Question is how much smaller. For example, it could be square root, 1 over square root of n, or 1 over n, or 1 over n squared. So the question: what's the functional dependence of alpha on n? So when alpha is small, we have here two terms. We have this term, the square root term, and we have the exponential term. So when alpha is small, which term is going to dominate? The exponential term. So we can, for the time being, forget about this term, where clearly the square root of 2 pi is not important. So we forget about this term. We just consider this term. And then we take a log of this and log of this. And if we do it, we find that alpha should be smaller than 1 over 2 log n. If we forget about this term and just think about this term. So this is a result that we expect if we do things formally, because this is the contribution of this term to this product being small is much smaller than this term. More formally, what we can do is we can take the log but do the whole thing, and eventually, after some algebra, the result that we obtain is that alpha should be smaller than 1 over 2 log n. This is the term that we think will dominate, minus half log of 2 pi. This should be from this 2 pi here, plus log n. This is a term that comes from the accuracy, or from this term here, plus half log alpha. So going from here to here is exact. There are no approximations. But now we can look at all the terms in the denominator and compare them. So clearly, log n is much larger than log 2 pi. So this term is much larger than this term, or from this term. So the only terms that remain is the log n term here, and here we'll have the log alpha. Let me write it explicitly. So if we think about alpha to be a 1 over log n term, this term is much smaller. This would be a term of log n. So the correction to the 1 over log n, this is what we expected by just ignoring this left-hand side of the product, is a log n. So in the limit, the result is that alpha should be smaller than 1 over 2 log n, or that the number of memory patterns in the network should be smaller than n over 2 log n. So the implications are that the signal-to-noise analysis that we did previously that resulted in saying that alpha should be on the order of 1 is correct up to corrections of log n. So if our requirement is that the probability of a mistake in a memory pattern, or the probability that not all neurons, the probability that in at least one neuron there will be incongruency between the input and the sign of the input and the sign of the desired input, the number of memory patterns should be smaller than n divided by 2 log n. What happens if the requirement is that we will have no mistake in no memory pattern? So this was the probability. In doing this analysis, we considered only memory pattern number 1. We wanted that the probability of a mistake for a memory pattern, the probability of a mistake in any neuron would be small for a particular memory pattern, for memory pattern number 1. But now, let's say that we want a small probability of mistake in any neuron in any memory pattern. How are we going to do it? What will change? Which term will change here? I'm sorry? Here. So what will change? What will change is the n. So we want this, we're considering the probability of a mistake in any neuron in any memory pattern. So the n will become Pn, large Pn. And if you do the whole calculation, it turns out that the effect on the result is rather small. The 2 will become 4. I leave it to you as an exercise. So 2 will become 4. That's the only difference going from the requirement of a small probability of a mistake for one particular memory pattern to a small probability of a mistake for all memory patterns. Alternatively, we can ask a different question. We can say, well, I don't care much about small number of mistakes in the retrieval. So why should I worry if thinking about a retrieval of a memory pattern? Maybe it is sufficient that, I don't know, 90% of the neurons will correctly retrieve the memory pattern, or 95% of the neurons will correctly retrieve the memory pattern. We don't really need 99.99% of the neurons to correctly retrieve the memory pattern. So we can do a different capacity calculation, this time making a weaker requirement. We just want a substantial fraction of the neurons to retrieve the memory pattern. We can relax the requirement. The problem is in doing so is the following. So let's say that we initiate all neurons in their activities according to memory pattern number 1. And let's say that 1% of the neurons in the network, the input to these neurons is incongruent with the desired input. The sign of the input is incongruent with this memory pattern. So once we let the dynamics of the network run, these 1% neurons will flip the sign. The activity of these neurons will change and become incongruent with this memory pattern. When these neurons change, they will affect the input to all other neurons in the network. So as a result of these neurons changing their activity, also other neurons may change their activity, because the analysis which we did assumed that all neurons in the network, that the pattern of activity of all neurons in the network is congruent with this memory pattern. If 1% of the neurons change their activity and become incongruent, then the input to all other neurons in the network may change. if this activity, if the input to all other neurons in the network change, then their activity, then more neurons can become incongruent with a memory pattern. And then we may have a positive feedback loop that eventually resulting in the network being in a completely different pattern. The computing, so this is a danger if we allow a substantial fraction of the neurons, if we allow mistakes in a substantial fraction of the neurons. It turns out that it's possible to compute the capacity in this case. So it is possible to compute the number of patterns such that a substantial fraction of the neurons the activity of a substantial fraction of neurons is still congruent with the memory pattern. We will not do this calculation, but it turns out that the maximal capacity is approximately equal to 0.14 n. So as long as the number of memory patterns, 0.14. As long as the number of memory patterns in the network is smaller than this 0.14 times the number of neurons in the network, then the memory patterns then fixed points that are close to the memory patterns are fixed points of the dynamics. And if we initiate a network in one of the memory patterns, it will converge to a fixed point that is very close to the memory pattern. If the number of memory patterns exceeds this fraction, then we have this positive feedback that eventually results in no overlap, results in a memory that is unable to retrieve any of the memory patterns. So this turns out to be the critical capacity for memory maintenance in this network. Questions? Yes.
Final expression for alpha and beta, they don't depend on the small n.
Right.
So it implies that in some sense we don't really care, or there's not a real significance to the tolerance that you define for that calculation. So it's not entirely clear how such a threshold comes about if you don't see, if you neglect doing the derivation anyway.
Because we have the log n. So the true capacity is order n. So the true number of patterns that you can store in the network is order n. The result that you get from these calculations is number of patterns is n over log n, or capacity which goes like 1 over log n. So this is so in that sense this is a conservative measure of the capacity, because you can tolerate an order 1 number of mistakes as long as this order 1 is like 1% or something like that. More questions? Okay, so what are the implications? So this model, the Hopfield model, I think is very interesting. It provides a framework by which the network can generate attractors that are arbitrary fixed point attractors, assuming that memories or memory states or attractor states are drawn from this distribution of plus minus 1 with the probability 1/2. And since the number of neurons in our brains, this number is relatively large, well, at least relative to the number of memories that we think that we have, this is an interesting framework of thinking about memory. Everything here is distributed, so memory is not stored in a particular neuron or in a particular synapse. All memories are stored in all synapses, which is an interesting property of the model. However, there are some issues with this. There are also some issues with this model, and to demonstrate some of the issues associated with this model, I'm going to consider this model when memories are distributed in a different way. So let's say that pi mu is equal to plus or minus 1, with probability f for 1 and 1 minus f for minus 1. So previously we're thinking about f as being equal to 0. I'm sorry, being equal to 1/2. Now we're considering a different value, or an arbitrary value of f. Now you remember the Jennifer Aniston results, and there we saw that not all neurons respond to all patterns, and in fact, it seems that representation in the brain is rather sparse. So each concept is encoded by a relatively small fraction of neurons, maybe 1%, maybe 10%, but definitely not half. So it'd be worthwhile thinking about this Hopfield model when the probability of plus and minus 1, these probabilities are not exactly equal to half, and we can use also this model as an exercise on how to compute capacity. So we did a capacity when f is equal to 1/2. Let's do it again. Let's repeat it when f is equal to when probability of 1 is different from 1/2. So let's do it. Ready? How I'm going to do it. So the way that we computed the capacity was by asking the question, given that all neurons in the network are in a particular memory pattern, what is the input to each of these neurons? Is the input to a neuron congruent with a desired memory pattern? So, for example, we consider the case of the activities of all neurons in the network to be equal to one of the memory patterns. Let's say memory pattern number 1. Let's look at the input. That's the input to neurons in the network when all other neurons have this memory pattern. So what's the input to the neuron? So this is equal to sum over j, jij, pj1. So this is the sum over all synapses, sum over all other neurons in the network, assuming that other neurons in the network are in memory pattern number 1, weighted by the corresponding synapse. So this is equal to 1 over n. We have sum over mu, sum over j not equal to I, pi mu, pj mu, pj1. This is jij, and this is the same pj1 as before. And what was the next step? Separate what? Cannot hear. Well, before that, we separated the synapse into this. We separated the synapses, or the synapses are constructed by adding many memory patterns. So we separated the first memory pattern, which corresponds or which is correlated with this current pattern of activity from all other memory, from the contribution of all other memory patterns. So this gave us 1 over n. Sum over j is not equal to I of pi1, pj1, pj1, this is mu being equal to 1, plus sum over mu larger than 1, or let's say mu from 2 to p. We have 1 over n, and we have sum over j is not equal to I, pi mu, pj mu, pj 1. And to see whether the input to the neuron is congruent with the memory pattern, we considered pi1 times hi. So let's look what we get here. So this would be, we have 1 over n, sum over j of pi1 squared. We have this pi from here. And pj squared, pi squared and pj squared are equal to 1. We have sum over n minus 1 terms divided by n. We take the limit of large n, so the first term will give us 1. And then we will get your z. So this would be plus 1 over n, sum over mu, sum over j, pi1, pi mu, pj1, pj mu. Okay. So far, so good. It's identical to what we did previously. What can we say about this sum? The sum of 1 plus 1 over n, sum over k, zk. So far, it's the same as before. What's the distribution of this sum? What can you say about the distribution of this sum? The sum of independent elements. All these are independent elements. So it should be normally distributed, as before. Okay. What's the next step? What do we need to compute about this distribution? Mean and variance. What's easier? What's easier? Mean. So let's start with the mean. So the mean of 1 over n, sum over k of zk is equal to 1 over n, sum over k, average of zk. Average of zk, as before, is equal to sorry? Now it's not equal to 0. Okay. Okay, now we have a problem because it's not equal to 0. Let's leave the pi outside. So this is, so we have pi1 outside. It's all. It's the same for. So we are going back to this term. So this would be equal to P I1. That's it. Times 1 over n sum over k of a product of three numbers. So we'll call these three numbers, I don't know, xi, let's leave it as xi. xk. So xk, what are the possible values of xk? It's a product of binary elements, so xk can be plus or minus 1. So it can be equal to 1 with some probability and to minus 1 with some probability. What's the probability of 1? Well, one possibility is that all of them are equal to 1. What's the probability that all of them are equal to 1? If it's 1 with a probability f, what's the probability that 3 will be equal to 1? F cubed. So it will be equal to 1 with probability of f cubed plus two are equal to minus 1 and 1 is equal to 1. What's the probability that this will happen? What's the probability that 1 is equal to 1 and 2 are equal to minus 1? Two of them are equal to minus 1. Almost. Three times. Why 3? Because the 1 can be the first element, the second element, or the third element. What's the probability of a minus 1? Well, as before, 1 minus f cubed plus 3 f squared 1 minus f. Now the average is clearly not 0, but let's compute it anyway. And for simplicity, let's consider the case of f being small. Let's take the limit of small f to gain some insight. In this case, this will be dominated by 3f, and this will be dominated by 1 minus 3f. Okay. So what can we tell about this term? What can we say about this term? This would be equal to pi1 times we will have n times p elements. We have 1 over n here. So we will have p elements times 3f times 1. This would be the contribution of this one, plus 1 minus 3f times minus 1. Which is equal to pi1 times p times 1 minus 6f. Sorry. Minus. Which will be dominated by this minus 1 term. So without considering the variance, the mean already kills us. So if we try to use this learning algorithm and encode memory patterns that are not equal to 1 or minus 1 with a probability 1/2, but that are equal to 1 or minus 1 with a probability that differs from 1/2, then the capacity is basically 0. If f is small, beyond one memory pattern, we cannot encode any memory patterns in this network. So this is a serious limitation of our model. Limitation that we will address next week. Questions about this? So computing the mean is sufficient to tell us that the memory capacity, when pi mu is equal to plus and minus 1 with a probability that differs from f, that the capacity is in fact 0.